Okay, Prof, Tuesday sessions, 2 o'clock to 2:50. We're going to change to 1 to 1:50 or 2. Okay, then there's the homework 3. Okay, and so that's due next Sunday. That is 2/5 Sunday. And then the following Friday, so we'll have the first midterm. Friday, I believe the 10th, at 2 to 2:50. So it'll be in this room and another room. So I did get a overflow room. And it will be chapters 1 through 3, homeworks 1 through homework 3. Okay, so when you submit homework 3 next Sunday, then we'll post the solutions, and then I'll have sessions. You'll have sufficient time to ask any questions. If you'd like, I could do a review session on one of the times that I have my sessions, so either Tuesday or Thursday, and then I could record that. You think you might want to review? Okay, several of you. So I'll announce that. Maybe Thursday. And then, okay, so this will be, I'll go over it more on the midterm later. But it'll be a closed text, closed notes. There will be one equation. There will be an equation sheet. So basically, the problems will be no numbers. Okay, and so no calculator needed. And then I'll post an old exam, okay, with the equation sheet. So you'll have an exam that is comparable. But basically, the two main topics, hydrostatics and Bernoulli equation. And within the 50 minutes, it's very limited, so I'll probably give you 2 problems, one of each, okay? And then you'll see on the old exam, it's likely the hydrostatics will involve forces on a submerged surface. Let's see, did I do that example problem? That actually was from last year's midterm, okay? And then some sort of Bernoulli equation, okay? And the topic that I'm going to talk about today, which is actually fairly limited, short, is very important though, okay? And so I may have an exam problem dealing with this, possibly, okay? Okay, but I think that's about it for the main announcements. All right. In homework, okay, so let me see here. There was, I think back here, okay, wait a second. Let me move this here. This was just okay, well, let's not move it. It's fine here. Okay, so Bernoulli equation, we developed last time from the streamline F equal MA streamline coordinates, and this was the component in the streamline direction, and we integrated along the streamline. So it's a very simple equation to use, algebraic. So we have P over rho plus V squared over 2 plus GZ is equal to a constant along a streamline. So in a particular flow, you can identify a streamline and the sum of these three terms would be constant along that streamline. Okay? Now, it's along that streamline. In general, if you choose another streamline, then this constant may be different. Okay? So you can't go across, you can't choose a point on one streamline and a point on another and apply it. So along a streamline, as indicated by the derivation of this equation, is very important. We also assumed these other conditions, that we have steady flow, that we have inviscid flow or frictionless flow. This is very significant assumption. All real flows have viscosity, so this is a real idealization. But a lot of problems, Bernoulli equation is not that bad, or at least explains, it's a simple explanation, a qualitative explanation of certain physical phenomena. Also incompressible, we assume density is constant when we derive this equation. Okay? And so one can apply this equation by, for example, identifying two locations along a streamline and then apply this to those two points. So the sum of the terms evaluated at one point is going to equal the sum of the terms, this constant, evaluated at another point. Okay? Now, I went over some examples last time, and I hope I have this. I threw a bunch of, okay, good. And so there is if you took a look at the homework assignment, there is homework 3.3, the third handout problem, that involves explaining this physical demonstration. And I hope that you're able to see it. It's a pretty simple one that you can do at home. So you have two, in general, you have two plates, okay, or two discs. And I chose one to be cardboard simply because when I put the straw in it, I want to have a fairly good fit so that I don't have leaking. Uh-oh. All right. Okay, so this cardboard from a manila folder seemed to work okay. Let's see if it works. If it doesn't, well, I'll have to do it over again. And then just another sheet of paper. So basically you have two discs or plates, okay? And I'm going to blow through the straw. And that will cause a flow. It'll go down and outward in between the two plates, okay? Now, if I'm blowing down and towards this sheet of paper, you would think that I would just blow it away, okay? And in general, if there's nothing happening with this sheet of paper, it's just going to fall to the ground, right? Okay, now I am blowing, I'm not sucking, and so let's see if this works. I'm kind of out of breath because I ran over here. All right. Okay, it sort of got there. Let me see. And I am blowing, okay? So, in fact, I was blowing so hard, I was getting lightheaded. Okay, so I want you to analyze this using the Bernoulli equation, and the sketch that I drew on the homework 3 assignment is basically explaining this, okay? I think I have a half of the figure on one of the views. But basically, you analyze the flow between the plates. Don't worry about the straw. So you've got, once it gets in there, you have this radial flow outwards. And that radial flow outwards is what I want you to analyze. And remember, last time when we discussed, a lot of problems involve both application of conservation mass and conservation of momentum, which is now Bernoulli equation. Okay? All right. And then also, remember when flow exits out of some confined region like a pipe or a jet and exits out into the atmosphere, which is what's happening at the outer radius, okay, the pressure there is atmospheric pressure. Unless I could blow so hard that we've got supersonic flow. It's going to be atmospheric pressure. All right? All right. But I encourage you to try this at home. Relatively inexpensive and simple. Okay. And then you can confirm that I wasn't sucking, I was blowing. All right. So that is the third handout problem. Okay. Let me get back to this. All right. Now, let me go back to this. This equation here, if you look at this equation, for example, this term, okay, v squared over 2. Well, you know that mv squared over 2 is the kinetic energy, right, from physics. So v squared over 2 is kinetic energy per unit mass. So this equation, the units are energy per mass. Okay, like this term here, Gz, you could think of it as potential energy per unit mass. So in fact, in MAE 11, we derived this equation from conservation of energy. And so one can think of this as conserving energy along a streamline. Kinetic energy, potential energy, and sort of a pressure, energy associated with the pressure. Now, the same equation, I indicated it here. So it's in particular conservation of mechanical energy. The thermal energy, because we're assuming frictionless, the thermal energy gets decoupled from the mechanical energy, and we're just left with mechanical energy is constant. But one can also multiply through by the density, and then since you've got pressure out here, each of the other terms has units of pressure. This first term is the true pressure, right? It is the thermodynamic pressure that we usually consider. But it's also referred to as static pressure. And the reason why it's referred to as static pressure is because when you measure it, if you move along with the fluid, then that would be the pressure that you measure. This term here, rho v squared over 2, okay, it's not a pressure, but it has units of pressure. It's associated with the velocity or kinetic energy, and it's referred to as the dynamic pressure. Okay? It's very important for you to understand this is the dynamic pressure. It's not a pressure, a true pressure, okay, but it is that term in the Bernoulli equation involving the velocity. And then finally, this can be considered or referred to as the hydrostatic pressure, okay, a pressure variation associated with elevation change. And the sum of the three we can consider as the total pressure. So you can think of the Bernoulli equation as the total pressure along a streamline is constant when you have all those conditions met: steady, inviscid, and incompressible. Okay? Now, I indicated previously that, okay, if you have this sort of flow, okay, and then the flow encounters some wall. So you could have a wall, you could have an object, such as this, and then here's the streamline that hits the center of that object, and of course, the flow there, it can't go through the object, okay? So that normal component of velocity has to be 0. And the streamline essentially splits off. And so one will go this, part of it will go this way, part of it will go this way. But at this point here, or at this point here, and here, is a point where the velocity is 0. We refer to this as a stagnation point. Okay? And if we can assume steady, incompressible, frictionless flow, okay, then if you take this streamline here and apply Bernoulli equation between a point upstream and this point here, the stagnation point, and then you assume sort of negligible, or you neglect the elevation. Okay, so we neglect elevation, and upstream, way far upstream, you could say we have P infinity or V infinity, or any pressure and velocity along this streamline. Okay, and then at the stagnation point, the velocity is 0. So we just have P naught. And I indicate the stagnation point with a subscript 0 or naught, okay, to indicate stagnation point. And this P naught, which would then be the combined static pressure and dynamic pressure, the sum of these two, actually anywhere along this streamline or far away, P infinity, V infinity, is referred to as the stagnation pressure. Okay, the stagnation pressure. And essentially, if the fluid here is moving with some velocity and is at some pressure, okay, and then encounters this point here where the velocity all has to go to 0, it's essentially the kinetic energy all goes to 0, but energy is conserved. Okay? So now all of that energy gets converted into pressure. So you can also think of the stagnation pressure as the highest pressure that could exist along a streamline. Okay? All right, so the stagnation pressure. So I want you to know and understand static pressure, dynamic pressure, hydrostatic pressure. The sum of these three is the total pressure, okay? And then we also have the stagnation pressure, which occurs at where velocity is 0, where the flow completely comes to rest and all that energy goes into the pressure. Okay. Now, a couple things about the measurement. So let me maybe redo this slide. Okay. And so let's say we have static pressure. So let's say we have some flow channel, duct or pipe, and we have the streamlines. Now, if it's a straight pipe or duct, then the streamlines are going to be straight. And as we discussed last time, if we apply the F equal MA in the direction normal to the streamlines, okay, then we have the partial P, partial rho, let's see, so we have partial P, partial N, minus rho G, this would be a dz dn equal v squared over r. Okay, I may be off, but the point being, this time, let's get it right, if you have straight streamlines, then the radius of curvature is infinity, so we don't have that centripetal acceleration. And so along the normal direction, it's just the hydrostatic pressure variation. Okay? Then, if you, for example, you could, oops, where's my eraser? Very carefully drill a hole on the side wall, and you could connect to a manometer. Fluid, and then like a U-tube even, so open to the atmosphere, so this would be P atmosphere, and then this is going to be and then if you chose this the center streamline, okay, so if this was 0.1, then you could just do the hydrostatic pressure variation, and this, relate it to the heights, and measure the static pressure at that location, okay? Because it's only a hydrostatic variation and not associated with the flow. Here in the notes, I indicated basically this, let's say you have here, if you have a gas, you could do something like this. If you have a liquid, in fact, the gas, you may only need this dimension here, the height of the column, and neglect the hydrostatic pressure variation in the gas. In the liquid, if this was liquid going through, then you would account for that. Okay? Now, what if you can't drill a hole in your pipe, or you have a curved passageway? So you could, or an alternative would be to use a static pressure probe. So now you have this very smooth, rounded tube closed, but now the tube itself, or the probe itself, has these static pressure taps. And then this whole thing could be connected to a manometer or to measure the pressure. And of course, this has to be very smooth. The probe itself should be very small, not to disturb the flow. And then you can conceive that a streamline would just follow the surface of the tube, and then you capture the local static pressure. Okay? Now, the measurement of the stagnation pressure. That is done using something referred to as a pitot tube. Okay? So now, if you have, again, a flow passageway, okay, and then there's just flow going through. A pitot tube looks like this. Okay? It's open so that the fluid will flow and enter in, and then the other end can be connected to a manometer. And when you put this in, the fluid's going to flow in, okay, and it's going to take a little time to equilibrate, but the fluid here within the tube is going to come to rest. So you cause a stagnation point here, okay, where the velocity is 0. Then upstream, or slightly upstream, is the streamline where you have the flow, the velocity, and the static pressure. Okay? And what you're going to measure, so if you apply Bernoulli equation to this streamline here, at this location, the pressure is the stagnation pressure because the fluid is not moving, right here in the tube. Okay? But upstream, the velocity has some value and the static pressure. So applying Bernoulli equation, you get P naught equal P plus rho V squared over 2. So the pressure you're measuring here is the stagnation pressure. Okay? So that's the pitot. This is a pitot tube. Now, a pitot-static tube, okay, sorry I'm using my notes here, but the main thing is I didn't want to have to reproduce these sketches from the textbook. So the pitot-static tube measures both. Okay? There's essentially a pitot tube here in the center, okay, where the fluid, once it comes to equilibrium, is going to come to rest here, and you've caused a stagnation point at point 2. But you have a concentric tube, and that outer tube, you drill your static pressure taps so that you also measure the static pressure. Okay? So you measure the stagnation pressure, the static pressure, and then you can connect each of these and here. So P4 is going to equal, this is the outer tube. So that's going to grab the static pressure. And then P3, you're going to measure the stagnation pressure. Okay? And if you apply Bernoulli equation, the relation between the stagnation pressure and the static pressure is this. Okay? And so if you then are able to measure the stagnation pressure and the static pressure, or the difference between these two, which is shown here. Here's the pedostatic tube, and the P3 and P4 here are now, you've got the connection to a U-tube manometer so that you can measure the difference between the stagnation pressure and the static pressure, which means this can be directly related to the velocity. So this is a way, the pedostatic tube, a way to measure the velocity. Okay? You might have one of these on an aircraft to measure the speed of the aircraft. So it's all, one can, the basic ideas from Bernoulli, but it would be calibrated, so there might be some correction, adjustment. Okay, so I want you to understand how one can measure the static pressure from static pressure tabs, okay? And the stagnation pressure, if I say, consider a pitot tube, I want you to understand what a pitot tube is to measure the stagnation pressure. And then the pedostatic tube measures both stagnation pressure, static pressure, and basically the difference, which can be directly related to the velocity. So the last homework problem, which is a text problem, a do but do not submit problem. Actually, all the do but do not submit problems are very important. Okay, but the last one deals with this. It's essentially a pedostatic situation, okay, where you measure the stagnation and the static pressure. Okay. Okay. I think I went over this idea where one can get a Bernoulli equation that is valid for unsteady and compressible, okay, is just leaving the unsteady acceleration term in the streamline coordinate f equal ma. And then when one integrates along a streamline, you have this, and if you don't assume density, and if you know how density varies with pressure, then that is the, you can account for compressibility. But you don't need to worry about this, okay? All right. And then maybe because we do have limited time, I'm just going to discuss a couple cautionary things about Bernoulli. As I mentioned, Bernoulli equation, the most used equation because it's so simple. You just want to use Bernoulli because it's so easy to plug and chug. But it's very limited. For example, here's our flow, very familiar flow that we considered at the very beginning, chapter 1. It's a shear flow, right? Now, could we apply Bernoulli equation from point 1 to point 2? No. Why? Yes?
The flow is not steady, that's why.
Sorry?
The flow is not steady.
Not steady? We actually did assume this flow to be a steady shear flow. Yeah?
They're on different streamlines?
They're on different streamlines. So this shear flow that we considered, okay, and we assumed steady, once it got going, it remained steady. The streamlines, if you looked at them, would be straight. Okay? So we're crossing streamlines, yes, but the more significant one is this is a viscous flow. The reason why the flow looks like this is all because of the no-slit boundary conditions because of viscosity. The fluid sticks to the walls. Okay? So if the bottom plate is stationary and the top plate is moving, which is how we got this, okay, then the fluid here sticks to the lower wall, velocity is 0. This fluid here is moving with the top wall, and you end up getting this linear profile. So it's, we cannot assume inviscid, and it's not along a streamline. Now, even this flow that we also considered in our homework problem, okay, develops in this way because of viscosity. So even if you choose a streamline, you can't apply Bernoulli equation. Even if you choose that center streamline, if you remember, the shear stress, which is the effect of viscosity, is mu du dy. And du dy right at that center line, if you evaluated it, was 0. Okay? So the effect of viscosity, the viscous shear stress, is actually 0 along that center streamline. Okay? So even though you choose that center streamline where the shear stress is 0, that flow is a viscous flow. So you can't cheat your way, oh, that one streamline is inviscid. Okay? No, the entire flow is viscous flow, and the pressure, which we may assume the pressure is uniform across over the entire area, the pressure varies because it's a viscous flow accordingly. Now, we may be considering flow through a pipe or a channel in your homework problems. Okay, so for example, I gave you an example where the flow flows out of a large tank. Okay, and even I think in the homework, I have you consider something like this, where the cross-sectional area may change. This is a large tank, okay? And maybe you can choose a streamline, that center streamline, and apply it here, maybe, to the, one location at the free surface, and the other location where it exits out to atmosphere, okay? But in general, if you have a flow such as the simple one, so I did this problem for you as an example, okay? Now, and this here was the end of the jet, or the pipe, a short pipe. But if we had a long pipe, then, and as we'll study more in detail in 1.1b, you could not, whereas if it was a short pipe and we cut it off here, okay, maybe we could assume inviscid, not too bad. But if it's a long pipe, it's the viscous effects are going to be there. And the reason, because when it enters into this pipe, the flow is, okay, in reality you do have viscosity. So you may have the no-slip bounded condition right at the wall, but for the rest of the flow, so at this location, okay, it's, maybe I should draw it like this. It's essentially uniform, okay? And so for some distance, you have a fairly uniform flow, and the fact that it's uniform, tau equal mu du dy, although viscosity is not 0, du dy is 0. Okay? So for a significant section across your pipe, the flow behaves as an inviscid flow, and it's uniform. But in reality, we have a thin region near the wall where viscous effects are significant. Because just adjacent to the wall, in reality, we're going to have the no-slip boundary condition, and the fluid is going to be stuck to the wall. Then it's going to be stuck to its neighbor. So eventually it's going to slow down the neighbor. And then that guy is going to slow down the next guy up. And so what you'll find, even though you have this uniform flow across most of the channel, you're going to have slowing down near the walls. So within this region, the velocity is slower. Okay? And so this region, which I'm indicating in dashed lines, is referred to as the boundary layer. Viscous boundary layer. It's a very thin region, but that's where all the shear is, and that's where all the action is. Okay? And it's usually, ultimately, it will not be negligible. But for these problems, if you have a relatively short pipe or channel, then the boundary layers are so thin, they're negligible, and you can assume inviscid flow. But if it's a long pipe, eventually these boundary layers are going to merge, and then you end up getting something that looks like this. And it'll be viscous throughout. So that's what this sketch in the notes was indicating. So as we'll learn more, again, in 101B, there's a so-called viscous, inviscid core. And as long as you don't have a long pipe, it may be reasonable to still assume Bernoulli equation to get pressure changes. There was a question over here? Yeah, so this fluid outside the boundary layer is called the inviscid core.
No, but the outside, like on the edges, when you move further down?
Oh, you mean within here, within the boundary layer? Yeah. It's a viscous flow. But as we'll learn more about it later, boundary layers can be very thin, okay? But they have significant implications on the flow. Yes? Expanding the area? Yeah. Expanding the area, you have to be very careful, because what happens is when you expand the area, the flow area is going to increase. And by conservation of mass, the velocity will decrease. Okay? And, the velocity will decrease, so the pressure will increase. And so you may, if you expand the flow enough, you're going to have a very high pressure that the fluid encounters. In fact, it may be higher than the upstream pressure, and that's referred to as some adverse pressure gradient, and then all hell may break loose. It may look something like this. And then we have our thin boundary layers, okay? And then when it encounters this so-called this pressure increase, the boundary layer separates, and you have these large recirculation regions. Okay, today what I wanted to do was show a video. So what I'm going to do is post a link to that video. And it is especially a very nice video. It's from the classic fluid mechanics films way back from ancient prehistoric days, 1950s. But they do experiments. They very clearly explain. And these ideas of the various pressures, pressure measurements, static pressure, stagnation pressure, is all going to be covered in this video. And so it's very important to understand the pressure, how it behaves. The video is very nicely explaining that. Okay? So look out for the announcement and link.